Let us look at what each of these surge protection methods mean in more tangible terms, starting with situations that may need energy to be diverted as the solution. The typical application is either the suction side of a pump station, that is at the downstream end of a long, large pipeline, or in other cases it may be a flow regulating valve at the downstream end of a long, large pipeline. To divert and absorb the available energy, we could use a surge tank, a standpipe, or a pressure vessel. How does energy diversion work when using a surge tank? While the system is carrying flow, fluid level in the surge tank floats up and down depending on the hydraulic level in the pipe system. Somewhere downstream of the surge tank, a valve will close or a pump will stop. When that happens, the flow is diverted and stored temporarily in the surge tank. Diverting flow into a low-height surge tank is often not practicable. For this solution to work, all the normal operating hydraulic grade lines throughout the life of the system need to fall within the height of the tank. During transient events, the system may need to provide overflow from the surge tank. Storage tanks tend to have a high capital cost, plus a relatively large footprint involving land requirements and visual social impacts. Using standpipes as an alternative overcome some of the problems found with surge tanks. How does energy diversion work when using a standpipe? While the system is carrying flow, fluid level in the standpipe floats up and down depending on the hydraulic level in the pipe system. Somewhere downstream, flow stops. Flow is diverted into the vertical standpipe and, if necessary, stored temporarily in a large component of the standpipe. Diverting the flow into small diameter standpipe can be more suitable for a few reasons. A standpipe can make use of the friction in small diameter piping to attenuate the surge, enlarge the structure towards the top to contain the fluid without overflow, economically build the structure to a greater height so that all normal operating hydraulic grade lines and surges are within the height of the standpipe. Some standpipes may still have to be designed to allow for overflow during transient events. Unless a standpipe can be as simple as a self-supporting piece of vertical pipe, more complicated standpipes can have a high capital cost. One very significant disadvantage of standpipes is that they are not pleasing to the eye, so the public tends to say, "Not in my backyard, thank you." The disadvantage of structures open to atmosphere, surge tanks and standpipes, has led to the popularity of closed, compressed air or nitrogen vessels. Pressure vessels are able to absorb kinetic energy in a compact, low-height format. How does energy diversion work when using a pressure vessel? While the system is carrying flow, fluid level plus gas volume in the pressure vessel adjusts to match the hydraulic level in the pipe system. Somewhere downstream, flow stops. Flow is diverted into the pressure vessel, gas volume decreases, and pressure of the gas volume increases. A significant proportion of the kinetic energy from the fluid is converted to energy stored in the compressed gas. In addition, flow rates out of the vessel into the pipeline can be throttled to constrain the rate at which energy stored in the compressed gas can be sent back into the pipeline. A closed pressure vessel can't overflow. They can empty and discharge gas into the pipeline if vessel fluid capacity is too small. Despite this, relatively inexpensive pressure vessels can be designed with compact modular layouts. These advantages have led to them becoming widely used to the point where pressure vessels of various sizes and pressure ratings are commercially available as commodity items. For the delivery side of a pump station, we can replace energy lost when the pump motor stops by using either a pressure vessel or a flywheel. Flywheels, once brought up to the pump's normal speed, become a source of stored kinetic energy When the motor stops for a period of time, the flywheel returns its kinetic energy into the fluid stream by keeping the pump turning. Flywheels, however, create a number of problems, such as increased loads on the electrical pump starting equipment, increased mechanical bearing loads and pump maintenance, occupational safety risks. Yes, you can put safety guards around a flywheel, but they can make that big red emergency stop button useless if they keep rotating for another 2 minutes, regardless of who and what has suffered an accident. Often at high rotating speeds, you can't design a flywheel with a big enough diameter without exceeding the safe rim velocity. Nobody wants pieces of disintegrated metal flying around a pump station. Providing the required moment of rotating inertia by making a flywheel longer increases the overall size and cost of the pump station. Consequently, flywheels tend to only be feasible on very small pumping installations. As a result, compressed air or nitrogen pressure vessels have become widely used as a source of stored energy on the delivery side of pump stations, for all the same reasons of modular compact format and cost that makes them popular when required to divert and absorb energy on a pump station suction main. What design choice can be used to directly reduce the size or rate of velocity change in a system? Start by selecting appropriate pipe diameters. Undersized pipes operating at high velocity dictate the magnitude of velocity change when a pump stops or valve closes. As the system grows, economics tend to favour increasing the system's flow rates. Consequently, the magnitude of velocity change tends to increase over time. Automatic control logic or manual operating procedures can be used to reduce the rate of velocity change by adjusting the time taken to stop-start a pump or open-close a valve. Pump speed control and rate of valve closure can be very effective during normal operation. Control logic cannot reduce the velocity change created by a power failure at a pump station. Often the pump power failure scenario is the one that governs surge protection design. We can protect a system against fast manual valve closure by installing a gearbox on the valve that physically forces the valve gate to close slowly.